for introduction. At first, we would like to start the overview of our research. This is very simple. We want to apply answer set programming called ASP to an combinatorial optimization problem, curriculum-based course timetabling. And yes, this is the application, the same as the previous talk. And what is answer set programming? It is general purpose approach to declarative problem solving. And it has a very good thing. It has combination of a rich yet simple modeling language and high performance solving capacities based on SAT. This is why we use ASP. And our target problem is curriculum-based course timetabling, so-called CB-CTT. This is one of the most studied course timetabling problem, as well as post-enrollment course timetabling. Also, there is an international timetabling competition called ITC, which is held in 2007. And then, our proposal in this research is the teaspoon framework for solving CB-CTT based on ASP. Our approach has two good things. One is ASP can be an ideal modeling language for course timetabling. Another one is here, ASP technology allows us to compete with dedicated implementations for CB-CTT solving. This is overview of our research. In the following, we will detail ASP and CB-CTT and teaspoon. In last, we will show the performance evaluation of our approach. Then let's move on to the ASP. ASP has its roots in database and logic programming and knowledge representation and reasoning. Also constraint solving, in particular SAT. And ASP allows for solving hard search and optimization problems, systems biology, product configuration, and so on. And ASP allows for solving all such problems in NP and sigma P2 in a uniform way. This diagram shows a framework of problem solving in ASP. When a problem is given, we somehow model it as a logic program, and we solve it and we obtain some model which is interpreted to the solution of the original problem. At first, we would like to explain what logic program is here in ASP. A logic program P is a set of rules of the following form. There are bodies and head. M is from 0 to N, and A here, and all BIs are atoms. This symbol denotes if, and all commas denotes and. So body is a conjunction. And we also have not here, which is default negation. Intuitive reading of this rule is if body holds, head must be true. Semantics is given by stable models, informally, which are sets X of atoms such that X is a classical model of a logic program P, and each atom in X is justified by some rule in P. This is the semantics. Next, let's look at an example of problem solving in ASP. We use classical graph coloring as an example. This is the input graph, and we have 6 nodes in this example. Then our goal is assign each node one color such that no 2 nodes connected by an edge have the same color. This is our goal. In other words, there are 2 constraints. One is each node has one color. Another one is 2 connected nodes must not have the same color. This problem can be represented in logic program as this one. We have 6 nodes, and we have some edges and we also have some color, red, blue, and green. And we also have two constraints represented by two rules of ASP. Here, we can say that each node has exactly one color, C. And the second constraint means the same color cannot be drawn for both edges of an edge XY. So this is very declarative and clear and very readable for problem. And in addition, good thing is that we can divide problem instance and problem encoding. This is very good feature. And then to get a solution, we run a program so-called Kringo. This is an off-the-shelf ASP solver. And after executing this command, we will get all solutions in very short time. Of course, this is a very easy example, but CPU time is not observable. And let's see an example of an answer. This is one answer. And it means that node 1 is colored by red, and node 2 is colored by green, and so on. So that's all for the explanation of ASP. So we have a very rich language and very powerful backend solvers. Then let's move on to our target problem, CB-CTT. CB-CTT is defined as a task of assigning all lectures of each course into a weekly timetable, subject to a given set of hard and soft constraints described here. The hard constraints must be strictly satisfied, and the soft constraints are not necessarily satisfied, but the sum of their violation cost, we call it penalty, should be minimal. So as you can see, there are many kinds of constraints. In addition, in CB-CTT, soft constraints are different in each formulation. Until now, 5 formulations have been proposed. This is a table explaining the formulations. So it means that, for instance, UD1 has a soft constraints S1, S2, S3, and their violation cost is 151. This is one formulation. But let's look at soft constraints windows. In formulation 3, it has violation cost 4, but formulation 4, violation cost is 1. And formulation 5, it has a violation cost 2. So the definition of soft constraints are different in each formulation. This is a very characteristic feature of CB-CTT. And this is a picture of our web portal for CB-CTT. This website has provided problem instances and solutions in different formulations. So there is 61 instances and 5 formulations, so which results in 305 combinations in total. And this website provides solution validators. Also, they provide visualizers. And the best known bounds on the web have been obtained by various methods, including meta-heuristic-based algorithm, integer programming, and SAT and MaxSAT, and many others. So various methods are tackling on this problem, and all best known bounds are maintained in the website. Okay, that's all for the explanation of CB-CTT. Then next, we would like to explain what is T-spoon. This is a framework solving CB-CTT with ASP. At first, T-spoon reads CB-CTT instances and converts it into ASP facts. Afterwards, these facts are combined with ASP encoding for CB-CTT solving. Finally, it is then solved by an off-the-shelf ASP system, Kringle, that returns a stable model answer set representing a solution. So if you are interested in ASP encoding, please let me know. I can show you later. So the main features of teaspoon encoding is one is compactness, in the sense that each constraint can be individually expressed in either one or two ASP rules. Extensibility, in the sense that easily extensible for switching constraints between hard and soft. And the third one is flexibility, in the sense that it is flexible enough in testing different formulations and supports not only single objective, but also multi-criteria optimization. And we want to say here that those features are useful and important for CB-CTT because CB-CTT has many kinds of hard and soft constraints and which are changed in formulations. And this is the reason why we say that teaspoon ASP can be an ideal modeling language for CB-CTT. Okay, now teaspoon is good for CB-CTT in representation. But the real question is, but is it good in performance? You may wonder, isn't it slow? So we would like to show the performance evaluation. For benchmarks, we use all 61 instances from the CB-CTT web portal with UD1 to UD5 formulations. So there are 305 combinations in total, and we give time limit as 3 hours for each. Here is result summary. Teaspoon improves or reproduces the best known bounds of all existing methods for 182 combinations. Indeed, this is nearly 60% in total. And the 182 combinations consist of 54 better bounds, including 16 new optima, and 128 same bounds, including 35 newly proven optimal. And in addition, teaspoon was able to produce upper bounds for very, very large instances in the category Erlangen with every formulation. And 24 of them were unsolvable before. Unsolvable means existing methods could not provide even feasible solution. Okay, here is the partial results for competition instances, competition 21 competition instances, and the column shows each formulation. You can see that for every formulation, we provide a red-colored figure, which shows our improvements. And yes, and each asterisk denotes that we provide optimality for that combination. This is the objective value for each combination. And we also would like to show CPU time for each combination in formulation 2, UD2. In this table, there is an instance and formulation and CPU time. So this time we give 3 hours for each instance, for each combination. But actually, in many cases, it provides optimal solution and optimality in very short CPU time. You can see that many combinations can be solved within 5 seconds. And for those instances, we observed that Klingo's answered core-guided optimizations are effective in finding optimal solutions. Okay, here is conclusion. We presented an ASP-based approach to solving CB-CTT. And the teaspoon program is available from this URL. And our future work is here. ASP encoding of timetabling, other timetabling. There are many kind of educational timetabling, such as examination timetabling, post-enrollment course timetabling, and etc. That's all. Thank you.
Questions?
Thank you for your talk. On the slide where you had the 5 formulations and the results, if you could go back to that.
This one?
Yeah, that one. So I'm just wondering if you have any intuition. So it looks like for under UD2, it doesn't improve any of them, ASP, and I was wondering if you had any idea why that was?
So I'm sorry, I couldn't catch your question. What is your question here?
So in the second column under UD2, it looks like answer set programming doesn't beat any of them.
Ah, okay.
And if you had any idea why.
You are wondering the improvements is less compared to the other formulation. Yes. Ah, okay, I see, I got it. Okay, and okay, I think there is one reason is that UD2 is the one of, I think, the easy formulation of CB-CTT. So there is, I think, I think there are many methods in this category. This is, and this is also a formulation used in 2007. So there are already many competitors, and they got already the optimal solution. That is one reason. But one thing we want to claim here is that for such UD2, we provide optimal solution in very short time. You can see that almost within 5 seconds, we provide optimal solution. So we start our research in such time, we can provide many fast optimal solution, I think.
Thank you.
Any other question? I just have one curiosity. Is your teaspoon approach, talking about performance, is your teaspoon approach more sensible to the size of the problem in terms of lectures and rooms, or is it more sensible to number of soft and hard constraints? So what affects more teaspoon? Size or number of constraints to?
Yeah, it's very good question. Of course, it is affected by the number of rules. So it's my feeling, but if I think UD5 has many soft constraints. So in such a case, the difference to the existing approach is a little bit larger than the other formulation. So I think if you have more kinds of constraints, I think it is strongly affected the performance of the ASP. But with regard to the size of the objective value, for instance, this RNA has the very large size of the objective value, I think more than 10,000 or something like that. But in this case, ASP is better than other approach. So I think yes, the answer is that the number of kinds of constraints. Yeah.
Okay, thank you. Okay, so let's finish the session here. Thank you.